What's your foray into well, now we can have some data. That's like an easy yeah. I don't have Sorry, this one. I need to go to. Sorry, I'm not talking down right now. I want anything. I want something. Stop your thing. I need to pay attention for it's kind of this is not.
Are you emceeing for me?
I am emceeing. All right. Did Eric get you all set up?
Oh, yeah. Yeah, I came down 20 minutes ago or something.
Good.
Mic and everything. The one here was on TV all the time.
Yeah, I know. I have a little thing about it.
Oh, I see. Yes, I'm a celebrity.
Yeah, you are. That's
Dude,
right.
I no idea how many times I get asked. I was at Aldi's and I'm standing.
Are you kidding?
Oh, no. I'm at Aldi's and I'm standing there and this woman is standing at the other register. She turns around and she goes, my husband says not to say anything, but are you that guy? I had another guy at Charlie's, the restaurant. He actually asked me a picture of me. He goes, I hope it's not going to be that I'm talking to you. And I'm like, Jesus.
You are. You're
I'm on power. I mean, you know.
You're the Toledo astronomer. All right. Let's get started. I am very pleased to introduce Mike Cushing from the University of Toledo as our final colloquium speaker of the calendar year. So Mike got his bachelor's in physics and astronomy from Boston University, and he then moved to the University of Hawaii at Manoa, where he received his PhD in 2004. Then he moved to NASA Ames for a year as a Spitzer Fellow and finished that fellowship at Stewart Observatory in Arizona. He was then an Intelligence Community postdoctoral fellow, interesting, at the University of Hawaii.
Tell you about it, but
you have to kill it, that's right. Followed by a NASA postdoctoral fellowship at JPL. 2011, he started as faculty at the University of Toledo and has been there ever since, instructed many students, including yours truly here. In that time, Mike has become something of the resident astronomy spokesperson for Toledo, Ohio. I still hear things from family members like, that Mike guy was on the news today talking about the meteor shower. Over his career, Mike's work has been instrumental in the discovery and characterization of ultra-cool brown dwarfs from the Spitzer and Wise era to the current era of JWST. So, take it away, Mike.
turn on my microphone. Thank you for the introduction, Adam. Thank you for having me. It's been a wonderful visit. I'm looking forward to speaking to everybody tomorrow as well. You have a really vibrant community here at Space Telescope, and please don't ever let that change. It's a joy for people who are at smaller institutions to come and interact with so many wonderful astronomers doing such exciting things. You know, I often, there's a couple places in the world I go to where I just feel astronomy. I feel a professionalness, a love of astronomy, and Space Telescope is one of them, and the other is Keck Observatory in Waimea. There's just something about that as well if you've ever been to Keck. So today I'm going to tell you about the fundamental properties and atmospheric chemistry of the coolest brown dwarfs with JWST. The work where I'm going to present to you has been done by a relatively small number of people. The original team was myself, Sam Byler, who was a graduate student at the University of Toledo. He's now a postdoc at Trinity College in Ireland. Adam Schneider is at the US Naval Observatory. David Kirkpatrick is at IPAC, Caltech. Along the way, we accreted some other people, including another graduate student, Harshal Kothari, at Toledo, Mark Marley, who's the director of LPL, and Sagnik Mukherjee, who's now at ASU as a 51 Peg Fellow, I believe. The work that I'm going to show you has been done primarily, almost exclusively, by 2 graduate students. And I don't know if that means that I have reached the peak of facultydom, or whether this is the beginning of the end of my scientifically useful life, maybe a little bit of both. So all of this work is done by Sam and Harshal. The roadmap for today is going to be, I'm going to introduce brown dwarfs, talk about the salient properties that relate to what I'm going to be talking about later, motivate our web program. We'll talk about late T and Y dwarf spectral energy distributions, which was the observational goal of the program. And then we'll talk about measuring fundamental parameters like bolometric luminosity, effective temperature, and then we'll talk some atmospheric physics and chemistry that we've learned based on these web spectra. Okay, so the salient properties and the web program. So we all know what a brown dwarf is, but just so we all start on the same page, it's an object who has not been able to achieve an equilibrium configuration wherein the surface radiative losses are balanced by energy generated in the core. So they don't fuse hydrogen, right? That's the simple version. As a result, they cool off over time. Unlike a star that lands in the main sequence and then sits there for a while, brown dwarfs continually evolve. This is a sequence of models showing the evolution of effective temperature as a function of age. So we have effective temperature on the y-axis starting at 4,000, which means the sun's up here somewhere at 6, going down to 0. Logarithmic age starting at 1 million years, going out to 10 billion years. Each line is the evolution of the effective temperature of a mass of different object. Sorry, of a object of different mass. So at the top, we have a 200 Jupiter mass object, or a 0.2 solar mass star. As it comes down its Hayashi track, it eventually reaches this equilibrium configuration. It settles in, finds a constant effective temperature, and then sits there for 1 trillion years or so. As you go down in mass, you eventually reach a point, something like 80 Jupiter masses, depending on metallicity, where you never reach that equilibrium configuration, and you simply cool off over time. And so once you're below 80 Jupiter masses, we call that a brown dwarf. I'm not going to get into the argument about what a planet is and whether it's at 10 or 1 or whatever. So just anything below 80 for our purposes is a brown dwarf. Because they cool off, that means they move through the spectral sequence as they evolve. So you might start out at a relatively massive brown dwarf, something like 2500 Kelvin. You'll be an M dwarf, then you'll pass through the L dwarfs, the T dwarfs, and then eventually into Y dwarfs. So unlike stars that we imagine sitting on the main sequence at a particular spectral type for a while, that's not the case for a brown dwarf, which means you can't just get the spectral type of a star and go to Allen's astrophysical quantities and look up its mass and its luminosity, because it changes as a function of time. At these cool temperatures, these atmospheres are composed primarily of molecules and condensates. So this shows you the mass fraction of the atmosphere as a function of temperature. So again, the sun is over on the left here, and we work our way down to whatever, 500 Kelvin or so. Once you get down to something like 3000 Kelvin, the mass fraction is dominated by molecules, and that just continues as you go to cooler and cooler temperatures. If you drop below 2,000, you pick up condensates. So these are particles that literally condense out of the gas phase and form dust, for a lack of a better term. The most important of these, for the atoms, it's potassium and sodium. These dominate the optical molecules. The carbon is locked in CO or CO2 or methane. Nitrogen is diatomic nitrogen or ammonia. You've got water, and then you've got trace species like phosphine or H2S. But the condensates, you literally can have hundreds of these species. An example of some of the most important from an opacity perspective is forsterite, liquid iron, sodium sulfide, chloride, potassium chloride, and water. And so when these condensates form, they can really alter the chemistry of an atmosphere. They not only remove the particular species from the atmosphere such that they cannot interact in chemistry later, but they also provide their own opacity, which changes the structure of the atmosphere. So they greatly complicate interpreting brown dwarf spectra. These particles that form in the atmosphere will gravitationally settle and form clouds in the atmosphere. So this is a sort of cartoon diagram from Katharina Lauder's. Stars are on the right, Jupiter's on the left, and as you cool off, you pick up more and more of these condensates. So sort of in the L's, you get some silicates and metal iron, and then as you go colder, those move down in the atmosphere and you pick up new clouds. And then as you go colder, those move down in the atmosphere and you pick up even more clouds. So on Jupiter, if you could fall through the entire atmosphere, it wouldn't just be the ammonia clouds or the ammonia hydrosulfide clouds that we see. You'd go through a water cloud and then cesium chloride and calcium chloride and all these other clouds as well. And modeling these clouds is a very difficult thing, right? We can't even predict the weather here on Earth 3 days in advance. Trying to predict the emergent properties of brown dwarfs with, with these many clouds is a difficult thing to do. As a result of the molecules and condensates, their spectra are distinctly not Planck functions. Nothing's a Planck function, but we often say stars are Planck functions. You just can't do that with these objects. So here's a sequence of models shown in black, along with their equivalent black body curve. And here are the temperatures and spectral types that go with them. And we're going from about 0.8 all the way out to 15 microns. And for the hottest objects, sort of M dwarfs, you can kind of see the Planck function sitting there. There's some absorption due to water and CO. But as you go to colder and colder temperatures, you really start to carve up the spectrum into these peaks that match the atmospheric windows on Earth, like Y, J, H, K, L, M bands. And you go really non-Planckian. So down here at 1,000 Kelvin, out in the near infrared, you are way super Planck function. But then over here, you're really sub-Planck function. And so interpreting spectra is just a really difficult thing to do. And then, when you get down to 400 Kelvin, there's nothing coming out of the near infrared. There's this sort of 5 micron peak, and then you kind of go out here. So they're really complex spectra. Another property that will become important in the story is that brown dwarfs have all the same radii. They are all effectively the size of Jupiter. So this is a mass-radius relation. I'm a solar person, so I look up here and look over here. If you're an Earth person, look over here. This shows you the mass-radius plot for various things. You've got stars over here. It's kind of like M goes as R, right, to sort of 0th order. You've got planets over here, and then you've got, in this region, brown dwarfs. So why is it that they have roughly the same radii? Well, it's a competition in the equation of state. So over to the right, if Zach had plotted them, there would be white dwarfs over here. And we all know that if you add mass to a white dwarf, it gets smaller. The mass-radius relation is inverted, right? Over on the left, we have planets. We have rock piles. So if you add a rock to a rock, it gets bigger. So the mass-radius relation goes up. And so the brown dwarfs fall in the middle. So you've got a function coming up, you've got a function coming down, and the brown dwarfs land where it's roughly flat. So all brown dwarfs to 0th order have the exact same size of Jupiter. So the summary of the properties you need to know is that brown dwarfs are similar in size to Jupiter. They have molecular-rich atmospheres that evolve as they cool. Everything that we have learned about brown dwarfs obviously comes from the emergent light of these objects. This is a plot of actual data from 0.7 to 15 microns of an M, an L, a T, a Y, and then Jupiter. All of this data has been obtained in various ways. There's Keck data, there's IRTF data, there's Spitzer data, there's Akari data, there's Subaru data. There's all sorts of pieces in here. And I have spent much of my life building up all of these spectral energy distributions over 15 years, me and other people trying to do this. When Y dwarfs were discovered, Spitzer was already warm, and so we had no access to sort of mid-infrared wavelengths. They're extremely faint. And so all we have is sort of in the pre-Webb era, we have some sort of HST data here. So we get sort of Y, J, and H peaks. We've got Spitzer and Wise photometry. And it turns out they're bright enough at 5 microns that you can do a little bit of rough spectroscopy with Gemini. And so Andy Schemer and collaborators have gotten spectra of objects out at these wavelengths. And so that's it. And it's really hard to infer fundamental properties of things when that's the light you get from the objects. So our Cycle 1 James Webb program. There were 3 goals. The first is to obtain broad wavelength spectral energy distributions of late type T dwarfs and Y dwarfs, so things colder than 1000 Kelvin. We want to compute precise, and I probably should have put accurate, fundamental parameters of bolometric luminosity and effective temperature. We want to compute the luminosity function, because we have L bol, and infer the underlying mass function from our luminosity function. And then we want to study atmospheric physics and chemistry using all the normal tools in our toolboxes, forward models and retrievals and that sort of thing. Today, I'm going to touch on 1, 2, and 4. My grad student who's now in Ireland is working on this paper now, and I hope that he's able to focus, now that he has a new job in a new country. So we'll see whether the paper gets written. So all I can talk about now is 1, 2, and 4. So the first goal, spectral energy distributions. We selected 24 objects from a clean 20 parsec sample. So we have the 20 parsec sample of all known L, T, and Y dwarfs. We started making cuts like they have to be solar metallicity-ish. They have to have no signatures of binarity. The parallaxes have to be relatively precise at fractional uncertainties of something like 5%. When we came, I forget what the total number is there. I should know that, it's been a while. 100 or so of these objects. We then plotted them in absolute Spitzer 4.5 versus Spitzer color. And the idea was pick targets that sort of span the color range so we can get a sense of the diversity of the objects across this color space. We did okay. There are some spots where you're like, why not get this thing down here? And most likely it was because it spilled over 75 hours. And we didn't want to fight in the large world. So we got pretty close to covering all of the range of color at a given absolute magnitude. The observations we proposed were to get NIRSpec prism to cover from 1 to 5 microns or so. If we needed HST, we could use that. We would then use MIRI LRS to go out to 12 microns, and then get photometry at 15, 18, and 21 microns. And then we would just drop a Rayleigh-Jeans tail to infinity to cover the entire spectral energy distribution. And so the gray there is a model, and then the red is smooth to the resolving power of the instruments. And so we basically cover all the flux, which is the point. So just as a reminder, this is the typical Y-dwarf spectral energy distribution before Webb. Again, Hubble, some photometry, and some spectra, you could argue, maybe just noise, but spectra. This is what you get in like 20 minutes of Webb time. And the young people just don't understand how frustrating this is. My students looking at this and just kind of, whatever, and the 3 old people are like, have dumb smiles on our face as we see this, because to be able to do this is just incredible, right? Like, it just blows our mind that we're capable of this. So this spectrum is just gorgeous. It exhibits all the important carbon, nitrogen, and oxygen-bearing species. Let's zoom in a little bit here. So if we zoom in at 3 microns, we actually found a new, the band isn't new, but we found it for the first time in these objects. It's the Q branch of the Nuon fundamental band of ammonia. It's this little divot here. And yes, you might say, well, that's pretty weak, but we see it in all the other objects. And so that was what convinced us that it's actually real. So we've got ammonia, a new ammonia band. Let's zoom in on the 5 micron region, which is going to become important to our story later. It's really rich with spectral features. We see water, we see CO, we see CO2, we see methane. It's a really complex region. So up in the color spots here are the cross sections for each of the molecules. So there's CO2 with the band gap, and then there's CO, and then there's methane, and then water just sort of covers everything. And then if you go out to 10 microns, you see the prominent ammonia band. It's not the first time this has been seen. Spitzer saw this back when we were doing Spitzer observations, but it's really clean. And Spitzer was never able to observe something this cold because it went warm before we found these cold things. The whole thing is, from 9 to 12 microns is just completely dominated by ammonia. And one of the cool physicsy things about this is that you have a double Q branch. And the reason why is because ammonia, it's inversion doubling. Ammonia is a triangle of hydrogen atoms with a nitrogen molecule that can be either on the top or the bottom. And the energy difference between those splits the lines and the bands, and so you get doublets everywhere, which is kind of cool. If you plot a sequence in spectral type, you get something that looks like this. It's reasonably clean out in the near infrared. This is, of course, where we spend most of our lives studying these things because we have ground-based telescopes and JWST. As you go out here, it's less clean, which is interesting, and I'll say a little more about that in just a little bit. Still beautiful, though. Okay, so let's talk about measuring these fundamental parameters. So we'll just do an object to explain how this works. Obviously, bolometric luminosity is d squared f bol. The whole point of getting broad wavelength spectra was so that we could integrate from 0 to 21 microns of our spectral energy distribution, and then we drop a Rayleigh-Jeans tail and we get some number of watts per meter squared. And notice that the Rayleigh-Jeans tail is only 5% of the bolometric flux. So we really are getting all of the flux of these objects. Previous observations were getting like 5% of the flux. So this is a huge improvement. Davy Kirkpatrick has spent years doing Spitzer follow-up observations to measure parallaxes of these cold objects, so we know its distance relatively precisely, which gives us a luminosity of less than 1 million times the luminosity of the sun. How do we do effective temperature? Well, we use Stefan Boltzmann. We have L bol. What do we do about R? Right? It's not like we can go out and use an interferometer to measure the radius of these objects. So how do we get R? Well, we talked about the fact that all brown dwarfs have roughly the same size. They're the size of Jupiter. So a nice nominal value that we can all just use as sort of a guide is assume 1 Jupiter radius, and so we get something like 450 Kelvin. It's a great nominal value, but we'd like to be a little bit more precise. And so we do something a little bit more complicated. This was first done by David Golomowski. The idea is we use models. Obviously, models aren't the thing you want to do when you're talking about measuring fundamental parameters. But the idea is that we understand the interior physics well enough that for bulk things like radius, we can trust them. So we'll say that. So what do? We use the fact that we know the luminosity. We don't know the age, but let's assume a broad wavelength, broad age range, right? So it encompasses almost everything from 1 to 10 gigayears. And then we can perform a Monte Carlo simulation where we just go into the models, we generate a random luminosity based on a Gaussian, we generate a random age based on a uniform distribution, and we pull out a radius. And we do that, whatever, 100,000 times or something. And this is the distribution that we get. And so there's the nominal Jupiter radius. And you can see that for this luminosity in that age range, really most of the radii are smaller than that. So if we can take our luminosities and our radii and we create a temperature distribution, this is what we get. And so, there's your distribution. That's what I should be sharing with people, but nobody wants ASCII tables. They want numbers and tables. So you can either take the median or the mean or however you want to describe it. There's a box and whisker plot if you're interested. And so we end up reporting a nominal version, the mean with 68% confidence intervals, or the median with the interquartile range. And so all of that information is in the paper. We can do this for all of them because it's just the same thing. We have distances. We can do integrals. And what this has allowed us to do is finally complete the calibration of the spectral sequence. Again, you can go into Alan's Astrophysical Quantities, or Eric Mamachek has a wonderful website with all of the calibrations for the spectral sequence. But the latest types were a problem because we just couldn't get their temperatures. So here's 3 ways you might show that. There's effective temperature versus spectral type, effective temperature versus absolute magnitude in 4.5, and then the same thing in H. And so it may seem like a small wing of this much larger thing, but there's a lot of power going on down here, especially when it comes to the mass function. Here is sort of a discussion of that diversity or that non-cleanness I mentioned. So we have two objects with the same effective temperature, and then we have another object with 100 Kelvin lower effective temperature. So in the near infrared, the black and the red look very similar. So that's two objects with 100 Kelvin difference in temperature. In the in the 5 micron peak, although not identical, the blue and the red look sort of similar. They're at least roughly the same height, and the black one is the one that's much more below. So maybe that kind of makes sense that they're similar temperature. And then you go out to 10 microns, and it's the blue and the black that look identical and not the red. And so, what we're seeing, I think, is the fact that all planets are not the same if they have the same mass and radius. You can't describe the planet and know all about it because you know its mass and radius, right? Every planet is unique. It's a great way to get, observing proposals is to say, well, everything is unique, but it's partially true. And these things are getting so cold that I think that's what's starting to happen, is that we're starting to see that there's just too much diversity in what can go on in an atmosphere to say, oh, effective temperature effectively tells you everything. All right, let's move on to the fourth goal, which is the atmospheric physics and chemistry. There are two complementary ways in which we model the atmospheres of cold brown dwarfs. The first we would call sort of a forward model. The idea is that you have a vector of parameters that is relatively small, so it controls the fundamental things like effective temperature, that controls the energy budget, surface gravity, which sets the pressure of the atmosphere, composition obviously is critical, and then you might tack on some other knobs and whistles for your model. You assume a lot of things like radiative convective equilibrium at every layer in the atmosphere. You assume some kind of chemistry. You assume abundances and anything else that's required. And then you run it through a radiative transfer solver, and you produce self-consistent temperature pressure profiles and emergent spectra, which can then be compared against data. So how well do these forward models fit the data? This is just for the people who care about specifics. It's a grid of models with lots of different parameters and knobs, and I don't want to necessarily get into them, but this is what it looks like because the big picture is the most important thing. So the data, again, is shown in black. The best fit model is shown in red. It's something like 450 Kelvin with a surface gravity of log of the surface gravity of 3.25 in CGS units. Overall, this fits pretty well, and if I had shown this model and this spectrum 20 years ago, modelers would have thrown a party because this is a really impressive fit. Nowadays, there's some issues here that we want to worry about. Here's 4 of them that are obvious. Down here in the near infrared, the model is too hot, and what I mean by that is the layers of the atmosphere from which we see light emerge at near infrared wavelengths is too hot. The air is too hot, and so we get too much light out in the near infrared. So something's wrong with the temperature pressure profile deep in the atmosphere. You'll notice that the model and the data deviate significantly, right around 4.2 microns. In particular, there's this whoppingly strong absorption. This is phosphine. The models predict a lot of phosphine, and we really don't see that in the data, so that's a problem. The log of the surface gravity is very, very low. 3.25 suggests a very young age, a very low mass. It seems to be a common thing when you fit forward models to these cold things. We don't quite know why or what the problem is. Could it be that low mass and that low age, or young of an age? Sure, but it's not near any moving groups. It's not near a young cluster, so you kind of think sort of field age, and this worries us. The other thing that was really surprising is if you just look at the model versus the photometry, they don't agree at these long wavelengths, and we have no idea what's going on there. In fact, I haven't even had a chance to really dig into this yet because we've been worried about all the other things we have to do, but that's a really interesting thing. Why is it that our photometry doesn't match the models there? And I should point out there's been other work done by Cindy Leggett. She actually fit all of our models with a different grid, and then this group in China also did a bunch of fitting for these. So if you're really interested to dig into the details, I would recommend you go look at those papers. So let's focus on the 5 micron peak. So if you recall, this region is really rich with features. You've got H2O, CH4, CO, and CO2. This is a figure, we need to talk chemistry for the moment. This is a figure in temperature pressure space. So temperature, pressure, or I should say temperature over here. This is some weird chemistry thing that I don't understand why they do this, but whatever. It's the carbon chemistry in temperature pressure space. So here is the log of the pressure of the gas. So 1 bar, the pressure of the air in this room is here at 0. It goes up to whatever, 10,000, and it goes down to 10 to the minus 10. And then temperature goes in some weird nonlinear way up here, something to like 400 Kelvin. And the solid lines are equiabundance lines. So if you fall on this line, that means you have equal abundance of methane and CO along the line. Now, the atmospheres of white dwarfs fall here, right? So high pressure, low temperature. And so this would suggest that CO and CO2 should not exist in these atmospheres, because they're just too cold. All of the carbon should be locked in methane. So the question is, why do we see CO and CO2 in these atmospheres? This is not something I should note, because I don't want to make it sound like we've done everything. This has been a problem for a long time. We know the answer, which I'm going to describe to you, and then we're going to amplify what we think we've learned since then. The generally agreed upon solution is that there's mixing occurring in the atmosphere. The atmospheres are not static. So imagine a static atmosphere. At the top of the atmosphere, you're shallow, you're very cool, and if you're cool, that means carbon is locked in methane, and there isn't much CO, so that you would expect to see methane. Deep in the atmosphere, where it's hot, you then move on that diagram down, and you will pick up CO dominating over methane. And so if you just imagine observing this object, the photospheres kind of appear. You should see a lot of methane, not a lot of CO. But let's mix gas around now. So imagine we start mixing the gas around on some characteristic time scale. Okay, so you bring CO-rich gas up, and you bring CH4-rich gas down. Okay, so that's one factor that goes into this. The other factor is that there's another time scale, which is the conversion time scale from CO to CH4. So it's going up, but it turns out that the rate at which CO is converted into methane is a super strong function of altitude in the atmosphere. In fact, it's like 15 orders of magnitude, going from seconds to like 1,000 Hubble times or something, right? The conversion time scale is really long, high in the atmosphere. And so when you combine these two things, what you find is that if the conversion timescale is longer than the mixing timescale, so you mix things faster than you can convert it, you end up with extra CO in the upper atmosphere, which you now can see. And so that's the explanation of why you see CO in these atmospheres. A point that we will return to is that there's something called the quench level. So this is the level in the atmosphere where the two timescales cross. And so the abundance of CO above this quench level is set by the abundance here at this quench level. So you can dramatically change the abundance of CO gas high in the atmosphere by this mixing, because it's set deeper in the atmosphere where it's more abundant. The same thing is true for CO2. So this happens as well. So how well do the models with this mixing fit this wavelength range? So here is 3.6 to 5 for a random white dwarf. There's the methane, there's the CO2, and there's the CO. Here's what the models give. Not horrible. Gets the methane right, gets the CO right, but really fails here at the CO2 band. In fact, it doesn't actually have any CO2 in it. It's entirely dominated by phosphine, which again, we don't typically see in these objects. So the question becomes, what's going on here? My student saw this and was talking to someone, actually it was here at an early JWST meeting, was talking to another graduate student, and they hatched an idea of how to try to figure this out. So they took this model here, and they said, okay, what happens if we change the C, let's change the CO2 abundance in various ways, and change the phosphine, and see if we can get a good fit. So keep the same temperature pressure profile, just change the abundances and see what happens. So if you increase the CO2 abundance by a factor of 5,000 and you decrease phosphine by something like a half, you get a better fit. Certainly that's true as you come up the peak and go down. So now this has been completely corrected. It still is a little deep here, and that's because the phosphine is still there. It still won't go away. But this is definitely a better fit than the standard out-of-the-box mixing models. So for some reason, we have to jack up CO2 by a factor of something like 5,000. Thousands is sort of the number to remember. So what do we think is happening here? The physical model that we proposed, along with Shen and Vischer, is that the quench approximation that we have been making is wrong for these two molecules. So what you're seeing here is the pressure of the atmosphere. So the upper atmosphere is here. As you go down into the atmosphere, you get higher and higher pressure. So deep atmosphere, upper atmosphere. And then the volume mixing ratio. This is a term that we use in atmospheres. It's basically the number density fraction. It's the fraction of atoms or molecules of a particular species given the total density. This is the prediction for a particular temperature. And so what does it say? It says, well, we should see a lot of methane here, right? So it's a small number, but compared to like these numbers, that's pretty big. So methane should be there. Here's the fact that in chemical equilibrium, as you go to higher and colder temperatures, the abundance of CO and CO2 goes down. That's what equilibrium predicts. Cold temperatures, carbon is locked in methane. The quench approximation is as follows. You find the level in the atmosphere where those two timescales cross, and then you say, okay, the abundance of that molecule is the same all the way up the atmosphere. So CO2 is now at like 10 to the minus 6, and that explains why we see CO2. CO is at like 10 to the minus 6, which explains why we see CO. The quench level for CO2 is higher in the atmosphere, which means CO2 quenches higher in the atmosphere, and so its abundance is still insanely small, which is the reason that we have to jack it up by a factor of 5,000 in order to see it. So what do we think is happening? It turns out that the reaction between CO and CO2 are very quick. They're basically tied to each other as the atmosphere evolves. And so once CO quenches, CO2 has to quench as well because their reaction rates are so quick, they just stay in equilibrium with each other. And so we get a factor of like 100 increase just by changing the way we model the quenching of these molecules. So this resulted in a release of a new grid of Elf-Owl models. I'm not going to read it, but it basically says CO2 should have been quenched with CO, and so we're going to change it and release the models. However, 5,000 is not 100. So, we're still an order of magnitude off. So we still think there's more work to do. We still don't quite understand why we're not getting a factor of 10 more in increase. But we think this is at least part of the story, that the CO and the CO2 quench together, and you've got to account for that in your models. All right, so we had these two complementary models. So we talked about forward models a little bit. The next kind of models are what are called atmospheric retrievals. Very similar, well, not very similar, but it's the same physics, it's just done differently. In this case, you have a vector of parameters, which is huge, like 19 parameters. The abundance of every molecule is a parameter. The mass, the radius of the object, which gives you gravity and sets the pressure of the atmosphere, is a model parameter. And then you have to model the temperature pressure profile through the atmosphere, which can have anywhere from 5 to 10 to, whatever parameters. You make no assumption of radiative convective equilibrium or the abundances because they're all free parameters. And then you optimize theta given the data, right? So the way when I'm trying to explain this to someone who isn't a physicist, well, is a scientist but not an astronomer, I would say it's like fitting a line to linear data, except the line is a spectrum, the data line is a spectrum, and the model line is a complex radiative transfer model. But you're doing the same thing. You're just minimizing chi-squared to find the best fit. I think it's important to write down our generative models when we do this, because I think a lot of what happens in retrievals is we start to get a little, what's the right word, impressed with our own magic. And it's important to be honest about what it is that you are modeling. And so this is our generative model. We say that our data is generated from an atmospheric model with a bunch of parameters like abundances and that sort of a thing, convolved with an instrument profile, multiplied by r squared over d squared, to scale the fluxes to Earth, and then we add a random variable epsilon here, which has a mean of 0 and a variance given by the uncertainties on the data plus a fudge factor that allows you to inflate them if need be. And we further assume that the covariance between the uncertainties is 0. So all data are independent, which makes the likelihood calculation easier because you're just multiplying Gaussians together. Again, this F value is the mixing ratio. It's the number density fraction, or n over x, and it is not a function of altitude. So it is a fixed value for the whole atmosphere. You do not allow the abundance of these things to change because it would just explode your parameter space to the point of being almost impossible to search. How do we determine theta? We use Bayes' theorem, right? Everybody has to say Bayes' theorem these days. I won't go into what all this is. There's no analytical solution, so we explore the posterior distribution using nested sampling at the Ohio supercomputer. This entire process runs in the Brewster retrieval framework, which was written by Ben Birmingham and Mark Marley. Ben's at the University of Hertfordshire in England. Just to give you a sense of how this process works, this is a temperature pressure profile plot. So pressure on the y-axis, low pressure, high atmosphere, high pressure, low atmosphere, and then temperature. So as you go into an atmosphere, you come down and to the right. Pressure and temperature both increase. What you're going to see in this animated GIF is this is the particular iteration that we're in. The red, which isn't shown, will be the median of the previous iterations. This shows you will eventually show you the parameter distributions for just 3 of the 19, so the abundances of water, methane, and CO. And then this shows you what happens as the model, as you're calculating chi-squared. So this is what happens under the hood of retrieval analyses. And I think it's going to slap back, so I'm just going to stop it there. So once we have optimized our parameters, we have 19 parameters to describe this atmosphere. Here's what the emergent spectrum of that model looks like compared to the data we found. You shouldn't be too impressed by this because there's so much freedom to these models that you can, I don't want to say you can fit anything, but you can fit close to anything. The residuals are good. They're not completely random. This is a systemic thing that we see in every retrieval. We think there's a missing opacity source, and there's some people in Texas working on that. We know we have a problem over here in the Y-band. We actually think that is a result of poorly modeled wings of the potassium and sodium lines that lie in the red optical. They are so pressure broadened that the wings of these lines go out, I don't know, 1,000 angstroms or some ridiculous number. They reach all the way into the Y-band. And the quantum mechanical calculation of pressure broadening of collisions of various molecules with these atoms is difficult, and it may not just be right. And so that's why we think that there's a really bad residual here. Some of this we think is our instrument profile as a function of wavelength. We had to we couldn't find it in any of the manuals, and so we sort of did a theoretical calculation, and we've been using that. And we really need to update to some sort of empirical thing once we have a moment. So the model fits reasonably well. We get incredibly precise temperature pressure profiles. So here we are, again, temperature pressure, high atmosphere, low atmosphere. So as you come in, you go hotter and higher pressure. The median one sigma interval looks like 20 Kelvin. If you did this with just HST data, it's more like 200 Kelvin. So we get a huge increase in the precision. And I say accurate there because at the end, I'll complain a little bit about all the systematics that we're not including. So it's precise. The question is whether it is accurate or not. What's so amazing about these Webb spectra is that they probe a tremendous range of pressures. Plotted on top of the temperature pressure profile are these sideways Gaussian looking things. These are what are called contribution functions. Every single wavelength has one, and it tells you where in the atmosphere the light you see at that wavelength is coming from. So the idea is you integrate over the contribution function from minus infinity pressure up to 0, and you obtain the specific intensity at the top of the atmosphere. So for example, down here, this Gaussian, when you integrate over that Gaussian in pressure, you end up with, and I don't know what wavelength that is, let's say 1 micron or something, you end up with the specific intensity at 1 micron. So it tells you where in the atmosphere the light at given wavelengths are emerging from. So if you just had near-infrared data, say from the ground or Hubble, you're really only probing down here deep in the atmosphere. Once you pick up Webb data, you get all the way up to 1/10 of a bar and even up to 100th of a bar, which is how we have such precise temperature pressure profiles. You'll notice that the minimum in the dispersion of the temperature pressure profile occurs where there's a lot of contribution functions, because we've got a lot of light coming from those regions, and it allows us to really constrain what's going on there. As opposed to down here, it's much broader and we don't have a lot of contribution functions. So Webb really probes, when you have these broad wavelengths, it really probes basically the whole atmosphere. How well do the abundances match the predictions of equilibrium chemistry? And the answer is well, and we understand when they don't. Here is the pressure, high atmosphere, low atmosphere as a function of the volume mixing ratio again. So very lots of molecules, not a lot of molecules. These are the CO2 and CO and methane that I showed you last time, but then we've got a couple more, and then we've got ammonia and we've got water. You might ask what's going on with these kinks here. What's happening is you're getting high enough in the atmosphere that water is condensing into ice, and you end up with a condensate. Now, we don't probe up there, so it's not too big of a deal, but that's what equilibrium chemistry would predict. So if you plop down our values, this is what we get. Methane and water generally match what you would predict. That's a good thing. CO and CO2, remember these are uniform with altitude, they are to the, they're sort of on the extreme edge of these curves, and that's because of that mixing. So we're getting, the fact that we see CO and CO2 says we have to have a large abundance, and we get a large abundance, perhaps not surprising. Ammonia does okay. The reason why there's this kink here is because ammonia also is impacted by non-equilibrium chemistry, although we didn't talk about it, so it changes the abundance. So we're generally happy with the abundances that we get from the retrieval. I want to end on phosphine. So cool brown dwarfs should exhibit phosphine in their spectra. This was a figure that I could not figure out how to remake. I apologize for the complexity of this. I don't know why chemists do this, but they love doing these. Ignore all the dotted things, if you can possibly do that. This is the same plot of temperature versus pressure. So 1 bar is here, high pressure, low pressure, high temperature, low temperature. And this is the phosphorus chemistry. So the solid lines, again, are equiabundance curves. And there's obviously a lot of different phosphorus-bearing molecules. If you put down where Y-dwarf atmospheres fall, they fall sort of along here. And so in principle, we should be able to see phosphine in these atmospheres. Jupiter and Saturn exhibit phosphine as well. Here is the cross sections for phosphine. The strongest band is at about 4.2 microns. And if you zoom into Jupiter's spectrum, there it is. There's the Q branch, there's the P branch, R branch of the absorption. So Jupiter, clear, and this has been known since the 70s. You can go back and find all sorts of great papers on phosphine. And the abundance, the mixing ratio is something like 1 part in a million, sort of, roughly speaking. So do brown dwarf spectra have phosphine? The short answer is no. But it's slightly more complicated, so I just want to lead you through the story. The first claimed detection was by Adam Burgasser last year. He was a part of the Uncover program, and of course, brown dwarfs are vermin for them. And so they found this brown dwarf, and he wrote a paper on a few of them, and he saw this dip here and just labeled it phosphine. It's a very low signal-to-noise spectrum, something like signal noise of 5. So I don't believe it. The idea is, well, there's CO2, there's some kind of absorption here, so that must mean this whole thing is phosphine. I'm not impressed. I think the community was sort of interesting. We should try to get follow-up data, but not the slam dunk that we were hoping for. Melanie Rowland, in the same year, was studying the coldest brown dwarf known. This is WISE 0855 at something like 260 Kelvin. She was performing retrievals on this object and found statistically significant, and I'll put that in quotes, evidence for phosphine at a level of 1 part in a billion. Just to give you a sense of where this signal is coming from, this is 3 to 5 micron spectroscopy, so G395H. Of this object, methane absorption, water absorption, that kind of stuff. If you zoom in around here, this is where the phosphine is, and this is the difference between a model with and without phosphine. Right? I mean, okay. She did all the right things, all the right statistical tests, did cross-correlation, still found it. So I'm putting sort of a light green yes there, like maybe. But it's hard to believe. We finally got one. Adam Burgasser, in his program to look at low metallicity brown dwarfs, found phosphine just spectroscopically without even blinking an eye. So this is the spectrum of Wolf 1130C. There is the Q branch, there's the R branch, and it's just obvious. It has phosphine in it. You can't argue with it. You see it spectroscopically. And that's at something like 10 to the minus 7. And so what I would argue is that, not argue, what I would say is that this is mostly what we see in all the other brown dwarf spectra that we've seen. We don't see an obvious phosphine feature here. So at the moment, 1130C is an oddball. We don't understand why it has such strong phosphine in it. One thought is maybe low metallicity, but we've got a lot of spectra of other low metallicity objects, and they don't show phosphine. So we really don't understand this object. And so I kind of ignore this for the moment in the larger story of phosphine. Our retrievals find phosphine in several objects. So we include phosphine in our analysis. And if you run a model with and without phosphine, this is the residual you get. And you get a bunch of noise at something like 4.2 microns, kind of lines up with the phosphine peak at 4.2 microns. But if you zoom in, there's the red and the green are the two different models with and without phosphine. And you again go, really? Like that's the claim? So the issue comes down to how you define detection. Like what's the criterion that we use for detection? There's a recent paper that came out by Daniel Thorngren, who had very strong opinions on how exoplanet people work on retrievals and how they report significances of various detections. We love this kind of paper, and so we decided to adopt its formalism, and their recommendation is to use the Aiken information criterion, or the Bayesian predictive information criterion simplified thing, which is just some equation that tries to quantify how one model is better than the other, and I don't want to get into the differences between them, but these are standard techniques used in Bayesian model comparison. So if you do that, and you take the difference between the two models, so you get a delta AIC and a delta BPIX. If it's negative, that means the model with phosphine is statistically a better fit. Okay, so these are very negative. And if you look at their table of what the numbers should be and how you can label them, they would label these as major discoveries. So, if you believe this, we have just 7 quintupled or 7-tupled the number of brown dwarfs known with phosphine detections. And this is what we put in here. That's why it's in quotes. And we say this is tentative. So we say we tentatively detect it because I just don't believe it. I don't think that this is real in the sense that I'm like, nope, I see phosphine. And the reason why is because this model, which I told you really needs to be written down, is just too simplified in my mind. What are the systematics that we are not including? Well, which line list did you use? Makes a difference. What is the sampling of the line list? If you sample the line list more finely, you'll get a different answer than if you sample the line list coarsely. That's not good. but it's true. What are the temperature pressure profile models? There are multiple ones out there. Some of them are just completely free, like ours. Other ones have penalties to keep things from wiggling. Others go and get the forward models and say, okay, I'm going to force it to basically look like this, but with a little bit of wiggle. And so what do you really learn? It seems to me you're just getting what you put in back. So that changes the answer. Our error modeling is extremely simple. We're assuming each pixel is independent and that we know the uncertainty in our error model. It's the data plus some fudge factor. That's not true. Are there correlated errors? Most certainly. We're not modeling that. And then how do you sample the posterior probability distribution? Do you use Markov-Chain Monte Carlo? Do you use nested sampling? How many walkers? How many this? What level do you go to? There's all these things that change the answers to the values that we get. And I have not varied each one of these to see the change, because that's something we're going to work on next, but I just think you should be aware of it. And so my opinion is no, these are tentative detections that require more work. So my summary, Webb is providing just stunning spectra of brown dwarfs, both this program and lots of other programs. We're able to measure effective temperatures of cool brown dwarfs to something like 20 Kelvin, plus or minus 20 Kelvin. The carbon dioxide chemistry was incorrectly modeled, and we at least have a step forward in improving that. We're not there, but we're getting close. And then retrievals are a really powerful technique to study the atmospheric physics, but you really have to take care in their interpretation, especially when you're starting to claim detections of molecules that you just can't look at the spectrum and go, yes, there's a molecule there. And I'll end there. Thank you.
All right.
Okay, sorry.
Time for some questions. Okay, first question. Yeah,
you pick.
Go ahead.
A great talk. So what has been the most useful insights you have gained that you believe enabled by the retrieval technique?
It's been the most useful insight. I didn't talk about it. Maybe I should have, since it's the most useful thing that I've gained. But the fact that the forward model temperature pressure profiles do not match the retrieved temperature pressure profiles. There is a difference, and we don't know why that is. So, and that's really the heart of it, right? Because that controls how the radiation passes through the atmosphere. So the fact that the two temperature pressure profiles don't agree is an issue. And we don't know, and that's future work, right? We just got to the point where we can say that. But there's something to be learned there. Because right now you get different answers using different techniques, and that's not a good thing. Yeah, I think I would say that.
Really great talk, thank you. My question is sort of related to the point you just brought up, but the phosphine that you're retrieving on, and it's sort of tentative about, how different is that from our equilibrium expectation of what the phosphine abundance should be? And I mean, my thought is that that phosphine just goes into a cloud condensate, right? And if the pressure profile of the atmosphere is different from the forward models, and there's a cloud, right, where that pressure profile has a kink, it's like we're all just sort of circling the point of, like, is there some phosphate cloud that we're all sort of dancing around, but no one's actually, here's the cloud.
So phosphine is also impacted by vertical mixing. So you get an enhancement of phosphine due to vertical mixing, which is why when you plot a mixing model, all the molecules are considered mixed at the same rate, and so that's why we see phosphine. So one possibility, somehow phosphine just is like, I don't want to party with CO and CO2, and I'm going to do something different. Maybe that's the problem. Another possibility, talking to Shannon, maybe we just don't understand the phosphine chemistry network. Maybe there's something in one of the equations that isn't right, the rate or something, and it just doesn't produce enough phosphine. It's mixed at the right rate, there's just too much. And then the third possibility that we talk about is the cloud, right? There are condensates that take phosphorus out of the gas phase. Maybe that's happening and we've got that messed up. We've got the condensation temperature messed up or something. So there's definite possibilities, and that's a chemistry. They got to look at their, and I think now that we've finally started to detect it, they're going to start looking at it more. And so hopefully in the next few years, they'll have an answer for what's going on with phosphine. I think there was a question over there.
Same question.
It's really exciting to see the bolometric luminosities for these objects. And I was wondering a little bit about inferring the effective temperatures. So if you're kind of using the evolutionary models to figure out a radius distribution, how much does that change if you use a different equation of state, or like their updates to equation of state? Would that like translate directly into the Teff?
Yeah, so yes, it would change the evolution. We only used one evolution code, and maybe we should have tried a different one just to see what the variance was. Clouds will also cause issues because it delays cooling. You know, the line we used to use was that it doesn't change, you know, what is it, like doesn't, between the worst case of dust and no dust, it only changed the effective temperature by 20%, but that was for hotter things. So it will change. It's a question of what's the dominant source, and my gut is that's not it, but we really should check. So maybe I should make my student go do that. The other thing is the age distribution. So we assume 1 to 10. You could go down to a half. It doesn't really change things dramatically, but if it's not uniform, now you're skewing things differently. And so there's some evidence that's come out by Trent Dupuy, Mike Liu, and Will Best, which suggests that the age distribution is not flat, it's some exponential thing. And so if we did in the paper include that, and you do get slightly different temperatures, not hundreds of Kelvin different, but you do get a different answer and a different distribution. So that's also in the paper as well. So if you're a uniform age person, you've got that. If you're a Will Best, you know, young population one, you've got the temperatures in that example as well.
Eric? Really neat stuff. So I mostly think about stars and galaxies, not this. But when you got to the point of saying, you know, look, they're all different, my next thought was what we would call chemistry, which is not at all what you call chemistry, right? Which is metallicity. So like that didn't really show up in your story. Is that the most important third parameter, or is in this space there's actually like other parameters that suddenly become important instead of the standard 3 for stars?
Yeah, I mean obviously composition does matter. So yes, and in fact, I was wondering whether this would come up. So we calculated our metallicity and our C to O ratio. Now I should say that this C to O ratio is only atmospheric, it's not bulk, and the reason why is because at hotter temperatures, silicate clouds form, like enstatite and forsterite, and rob the atmosphere of oxygen. So there's oxygen trapped down below the photosphere where we can't get access to it, and the correction's like 20%. So it seems super solar, which is a bit weird, so we don't quite understand that. But even if you don't believe the absolute value, there is a spread. And so, yes, certainly the bulk metallicity matters, but then the mixing matters, and you know, maybe each molecule mixes at a different rate. There's just so much extra stuff going on that, you know, metallicity is certainly a part of it, but there are other things as well.
It sounds hard. You should work on stars.
Yeah. Oh, yeah. No. It's yes. These are hard, but they're fun. So.
Are these metallicities that you're measuring, I mean, is it the same? You say there's all this extra stuff going on, right?
Yeah.
Is it the same as the metallicity I would measure if I went and looked at a star?
Yes. So what we do is we assume you know, what do you've got? You've got carbon monoxide, carbon dioxide, methane, ammonia, and water, right? C, N, and O are the biggies, and so they dominate in the metallicity. And so we just add up the numbers of each of the, you know, how many carbon, how many this, and we do the math, and we can add in other things, but it doesn't change much. So yes, but maybe not like the way you're thinking about it. Yeah.
Okay. I think we should cut it there, but ask more questions on Mike at STAS in a few minutes here. Let's thank Mike again.